Hello, welcome to all of you. Now we discuss modified Lotka-Volterra model for biomathematics, semester 5, paper D.Sc. U1, Mathematics Honors, University of Calcutta. Consider the following modified Lotka-Volterra model. This d capital X dt equal to r capital X bracket 1 minus x capital X by capital K minus b capital X capital Y dy is equal to minus dy plus c x y capital Y, where r, capital K, B, C, D are positive parameters. Using the substitutions, small x equals to capital X by capital K, small y equal to B by R into capital Y, and T equal to R into capital T. Reduce the above system in the following dimensionless form. d small x dt equals to small x bracket 1 minus small y, and d small y dt equal to beta small y bracket x minus alpha bracket close, where alpha beta are new parameters to be determined. Find all steady states of the dimensionless system and discuss their stability. Here, the given system, modified Lotka-Volterra model, is this. Call it 1 and 2. This is the modified Lotka-Volterra model. This. Now we substitute small x equals to capital X by K, small y equal to this, and t equal to r t by this. So we differential coefficient dx equals to d capital X dk, dy equal to b d capital Y d by r, and dt equal to r d capital T. So this equation 1 becomes dx. So we put k into d small x, and d capital T, we can put this 1 by r d small t, and r into capital X from this, and 1 minus capital X by capital K. So put capital X equal to small k, okay, so k into capital small x, k into small x by capital K, minus b into value of capital X is k into small x, and capital Y equals to r by b into small y. After simplification, we get d small x dt equal to x 1 minus x minus y. So we will get this first equation, this, call it 3. Then equation 2, actually it is called 2. So this is actually 1. This is actually 1. This is 1, and this equation is 2. This equation is 2. Then similarly we can get d capital Y, d capital T. So d capital Y from this is equal to r by b into d small y. So r by b into d small y, and dt by r equal to minus d capital Y. This minus d parameter, positive parameter d, r by b into small y, and plus c capital X capital Y. So value of capital X is this, and capital Y is this. After simplification, we get this dy dt equal to, taking common, kc by ry x minus d kc. Say this kc by r equal to beta and d by kc equal to alpha. So we get new equation 4, dy dt equal to beta y bracket x minus alpha, where alpha equals to d by kc and beta equals to kc by r. Thus, we have dimensionless system of the given modified Lotka-Volterra model. dx dt equals to x bracket 1 minus x minus y dy dt equal to beta y bracket x minus alpha, where alpha is this and beta is this. Now, to find steady states or equilibrium points, we must have the dx dt equal to 0 equal to dy dt. So, from the system 2, dx dt equal to 0 means x 1 bracket 1 minus x minus y equal to 0, and dy dt equals to 0 gives beta y bracket x minus alpha equal to 0. Hence, either x equals to 0 or 1 minus x minus y equal to 0. And from this second equation, beta y equal to beta positive parameter, so obviously either y equal to 0 or x minus alpha equal to 0. So if we put x equal to 0, we get this y equal to 0. So we get steady states, three steady states. First is one trivial steady states 0, 0, call it E0. And if we put x equal to alpha in this equation, so put x equals to alpha here, then y equal to 1 minus x, that is 1 minus alpha. So this is the, for x equals to alpha, we get the E star. E star is the coexistence equilibrium point, existence of alpha 1 minus alpha. And if we put y equal to 0 in this equation, then we get x equal to 1. So we get E1 steady state 1, 0. So ultimately we get find three steady states 0, 0, 1, 0 and alpha 1 minus alpha. Now clearly Easter feasibility of Easter, existence of Easter, if 1 minus alpha is greater than 0, that is alpha is less than 1, because alpha is positive parameter. So obviously 1 minus alpha is greater than 0. This is actually this is a biological model. So obviously 1 minus alpha greater than 0, we find alpha is less than 1 for existence of this Easter point. Let fxy dx dt equals to called fxy and dy dt is equal to called gxy. So fxy equal to x into bracket 1 minus x minus y and gxy equal to beta y x minus alpha. Then del f del x, del f del y, del g del x and del g del y. We'll find all these and then find the Jacobian capital J for these equilibrium points. We get fx, fy, gx, gy. So this 1 minus 2x minus y minus x beta y beta into x minus alpha. Now value of the Jacobian J for the trivial equilibrium point 0, 0, J 0, 0 equal to, put x equal to 0, y equal to 0, we get 1, 0, 0 minus alpha beta. So eigenvalues of this system for the steady states, this we get 1 and minus alpha beta. Since eigenvalue 1 is positive and this minus alpha beta is negative, so we get unstable, actually saddle point. Is stable for this minus alpha beta eigenvalue and unstable for one eigenvalue, positive eigenvalue. So actually get this steady state 0, 0 is a saddle point, that is actually unstable steady state 0, 0. Next, for the steady state 1, 0, j at the point 1, 0 equal to minus 1, 0 beta 1 minus alpha. So obviously for this upper triangular matrix, these eigenvalues are diagonal, principal diagonal elements minus 1 and beta 1 minus alpha. Minus 1 is negative, and for negativity of this eigenvalue beta 1 minus alpha, beta is positive quantity, so 1 minus alpha is negative. So 1 minus alpha is less than 0, that is if alpha is greater than 1, then both eigenvalues are negative, and then this steady state 1, 0 is locally asymptotically stable if alpha is greater than 1. And by Raoult-Hartree rule, we can say that unstable for alpha less than 1. Now, for this coexistence equilibrium point alpha 1 minus alpha, this j alpha 1 minus alpha is this, Jacobian is this. Obviously, in this trace of this g at the point alpha 1 minus alpha, obviously minus alpha plus 0, so obviously it's negative, trace is negative, and the determinant value of this, this into this minus this into this, so alpha beta 1 minus alpha. Here, for feasibility of star, we must have alpha is less than 1. Hence, obviously, alpha beta 1 minus alpha is greater than 0 because alpha is less than 1, so 1 minus alpha is greater than 0. Alpha beta positive quantity, so alpha beta bracket 1 minus alpha is obviously greater than 0. So this trace is negative, but the determinant value is greater than 0. So a coexistence equilibrium point star is locally asymptotically stable if alpha is less than 1, and unstable if uh, alpha is greater than 1. So actually this is greater than 1. Sorry, this is greater than 1 actually. Alpha is greater than 1. So for this, now the characteristic equation for this star, for this matrix minus alpha beta 1 minus alpha 0. So I characteristic equation is this. So minus alpha minus lambda and 0 minus lambda. 0 minus lambda is this. So this is the quadratic equation for lambda. We get lambda square alpha lambda plus alpha beta into 1 minus alpha equal to 0. So there are two eigenvalues, lambda 1 and lambda 2, given by this minus alpha plus 1 root over of this by 2. Clearly, discriminant b square minus 4ac equals to alpha square minus 4 beta alpha bracket 1 minus alpha is greater than 0. And so alpha is greater than 4 beta minus 4 alpha into beta. Hence, alpha into 1 plus 4 beta is greater than 4 beta, taking alpha common, and obviously alpha is greater than 4 beta by 1 plus 4 beta. So, discriminant is this. When discriminant is positive, then value of alpha is greater than 4 beta by value of alpha is this 1 plus 4 beta. So this is stable, star is stable if alpha is greater than 4 beta by 1 plus 4 beta, because discriminant is greater than 0, and stable focus if alpha is less than 4 beta by 1 plus 4 beta. And either here alpha is obviously less than 1. In this case, alpha is less than 1. So under this case, alpha is less than 1, and when alpha is less than 1 is asymptotically stable. But when alpha is greater than this, 4 beta by 1 plus 4 beta is stable node. If alpha is less than 4 beta by 1 plus 4 beta is stable focus. Now we study the zero growth isoclines for this. Here, y-nar clines means the dy dt equal to 0. Actually, dy dt means the vertical component of the velocity is 0. So dy dt is the vertical component of the velocity 0. So this y equal to 0 and x minus alpha equal to 0, because dy dt equal to is beta y x minus alpha. So dy dt equal to 0 means y equal to 0 and x minus alpha equal to 0. So on these lines, y equal to 0 and x equal to alpha, dy dt equal to 0. So on these lines, vertical component of the velocity is 0. So this y equal to 0 means the this x-axis, and x equals to alpha means this line. So this is the actually this is the horizontal component exists on this line, on these two lines. Horizontal component of velocity exists, dx dt. So we find dx dt for this y-nar lines. This dx dt is equal to x into 1 minus alpha on y equal to 0, because y equal to 0, put here y equal to 0. So this dx dt is positive if 0 less than x less than 1. So when 0 less than x less than 1, so for this part from 0 to less than 1, for this part, this dx dt is greater than 0. So horizontal component of velocity on the y-nar line y equal to 0 is positive, dx dt is positive. So put here right arrow from the 0 to 1, from the 0 to x, 0 less than x less than 1 for this part. This is the positive, dx dt positive. This is the horizontal component of velocity positive. So I put here right sided arrow here. And this dx dt is negative on this y-nar lines y equal to 0 for x greater than 1. So this is negative. So put here left-handed arrow for this part. So after x equals to 1, or x equals to x when x is greater than 1, I put left-handed arrow this, left-sided arrow is this and this. And for the other null lines, x minus alpha equals to 0, then this divided to 0. So vertical component of motion is 0. So horizontal component value dx on this null lines x equals to alpha, put x equals to alpha on this. So we get this. So obviously this horizontal component dx is positive when 0 less than y less than 1 minus alpha, because here 1 minus alpha is less than this y is greater than 0 and y is less than 1 minus alpha, then this quantity is positive. So for this 0 less than y less than 1 minus alpha, 0 less than 0 less than y, 0 less than y is y axis and 1 minus alpha, this point is 1 minus alpha. So for this part on this straight line, for this part, this is the right-handed arrow. For this part, this is the right-handed arrow for this part, because this is dx is positive for this part, and this negative dx negative for the null lines x equal to alpha when y is greater than 1 minus alpha. So for this part, y is greater than 1 minus alpha means this part is the left-sided arrow, left-handed arrow on this part to this horizontal component of the velocity on these y null lines x equal to alpha. Similarly, on the x null lines means dx dt equal to 0, where the horizontal component of velocity is 0 is called x null lines. Then x null lines are x equal to 0 and 1 minus x minus y equal to 0. So x null lines here, x equal to 0 means the y axis, and 1 minus x minus y equal to 0 means this straight line passing through the point 1 0 and 0 1. So this is the x null lines. On these straight lines, horizontal component of velocity dx dt 0. So vertical component of velocity dy dt on this those straight lines is dy dt equals to put x equal to 0, on this line is minus alpha beta into y. Obviously alpha beta positive, so this is negative for y greater than 0. So y greater than 0, this is negative. So obviously put here down arrow for y greater than 0 portion on this x null lines, on this x null lines y equals x equals to 0, and this positive when y is negative. So for this part, this portion, this upsided arrow, upwards arrow put for this below portion when y is less than 0, and dy dt equals to beta y 1 minus y minus alpha for this part on the part on the line, on this line 1 minus x minus y, 1 minus x minus y. So this dy dt is positive for 0 less than y less than 1 minus alpha, 0 less than y less than 1 minus alpha, 1 minus alpha, 1 minus alpha is this portion. So for this portion is the positive quantity. So for this portion means 0 to 1 minus alpha. So this portion, from this portion here positive, dy dt is positive. So put upwards arrow for this portion of the straight line on the x null lines, and this dy dt negative for when y is less than 1 minus alpha. So y is less than 1 minus alpha, no, sorry, y is greater than 1 minus alpha, this is negative. Oh, y is greater than 1 minus alpha, y is greater than 1 minus alpha, this 1 minus alpha y equal to 1 minus alpha, this, so greater than this when y lies in this portion. So for this straight line, on this straight line, put here negative value dy dt, so put downwards arrow. So by this clients, isoclines, we get this picture for this here. This steady states 0 0, steady states 1 0, and steady states alpha 1 minus alpha. Now we study for the phase portrait when alpha is greater than 1. When alpha is greater than 1, then this x equals to alpha, actually draw we x equal to alpha greater than 1. So beyond this line, this, and we get only two steady states, 0 0 and 1 0 here. So phase portrait of this, clearly E00 is unstable saddle node, and E10 obviously locally asymptotically stable, and Easter alpha 1 minus alpha coexistence we have does not exist for this, which is non-feasible here. Actually, the Easter alpha 1 minus alpha exists for the fourth quadrant. Actually, this straight line and this straight line intersect where this point is alpha 1 is actually fourth quadrant, so it is not feasible here. And when alpha is less than 1, but alpha is greater than 4 beta 1 plus 4 beta, and in this case, this alpha x equals to alpha is left side straight line, left side parallel straight y axis, this x axis and this y axis. So for this alpha, we get this coexistence equilibrium point is here. Obviously, stable equilibrium point is, but 0 0 unstable and 1 0 is also unstable here. Only stable point is this alpha 1 minus alpha is the stable node here for this point. And figure 4 describes when alpha is less than 1 and alpha is less than 4 beta 1 minus 1 plus 4 beta. And then this straight line passing to this point and this x-axis, this y-axis. So this is the 0 0 is the um, 0 0 is the steady state, and this alpha 1 minus alpha is steady state, and 1 0 is also another steady state here. So clearly, this step with this equilibrium point is a stable focus here, but this 1 0 unstable and 0 0 unstable here for this case. Thank you. We stop here, but this right here, this is the x-axis, this x and this y-axis here, and this is the unstable uh, point, and this is also unstable. Only stable focus is this e e e star alpha 1 minus alpha. Thank you.